This video we're going to talk about curve sketching. Basically it's a culmination of everything that we've been working towards. So if I have a function, I can know a lot about the graph of that function through the use of our first derivative test, our concavity test, knowing how to find asymptotes and intercepts and things like that. So I'm going to go through this first page, just kind of informational guidelines for sketching a curve, and then we'll look at an example. So when you are going to sketch a curve, first you're going to look at the original function, and you can find some information about your graph through the original function. One, you can find the domain, especially if it's a polynomial. It's very easy. But remember, the domain is the x values that can be plugged in to the function. So oftentimes the easy way to find the domain is to focus on what cannot be plugged in. So in the case of like a rational function, you would want to make sure that you're excluding any x values that would make the denominator 0. You can also find the x and y intercepts. For the y-intercept, you would plug in 0 for x, and for the x-intercept, you just plug in 0 for your y. And then you can also find asymptotes. Vertical asymptotes occur for rational functions when the denominator is going to equal 0. So we'll look for that. And then also horizontal asymptotes if we do the limit as x approaches infinity or negative infinity, and we get an answer for that, then we will have a horizontal asymptote at those values. Okay, so using the original function, we're going to check all of that information. The first derivative, I can think about the first derivative test, right? So that's going to tell us where we have intervals of increase and decrease, and where we have some local maxima or local minima. So those are going to be located whenever our increase to decrease, whenever we change from increase to decrease or decrease to increase, we're going to look for those local extrema. The second derivative will tell us things about concavity and points of inflection, right? So it'll tell us when a graph is concave up or down, and then if we have a switch in concavity, those are going to be where we have points of inflection. After finding all that information, you should have a lot of information about the graph that you can help guide you to getting a very accurate depiction of that graph. So I'm going to look at the function y equals x cubed plus 6x squared plus 9x. This is a polynomial, but I'm going to go ahead and look at this, and I'm going to find all that information, and then I'm going to sketch the graph. So from the original function, the information that we were looking at was the domain. So since it's a polynomial, the domain is all real numbers. We also can find the x and y intercepts. So to find the y-intercept, I'm going to plug in 0 for x. So that's going to be 0 cubed plus 6 times 0 squared plus 9 times 0, which would give me 0. If your y-intercept is at 0, that means your x-intercept will be at 0 as well. Now we could have multiple x-intercepts. And a lot of times when you go to find x-intercepts, sometimes it's more challenging than what it's worth. But I want to plug in 0 for y, so I set this function equal to 0. I'm going to factor out x. So we have x times x squared plus 6x plus 9 is equal to 0. This trinomial I can factor into x plus 3 times x plus 3. And so that means that I have x-intercepts at x equals 0 and at x equals negative 3. And then we can find asymptotes. So vertical asymptotes, it's a polynomial. The domain is all real numbers. You're not going to have any vertical asymptotes. But watch for that if you have a rational function. You want to make sure that you know how to find those. And then horizontal asymptotes, again, same thing. If it's a polynomial, you're not going to have any. But the way you find horizontal asymptotes is you do the limit as x approaches infinity. of your function. And I think this one's easy to see, that if you were to evaluate this at infinity, you would just get infinity, which means that there is no horizontal asymptote. So the original function tells us all of that information: domain, x and y intercepts, vertical asymptote, horizontal asymptote. I'm going to go ahead and plot some of that information. So I've got a y-intercept, also an x-intercept at 0, so I know that it's going to cross through at 0, 0. I also know that I have an x-intercept at -3. Okay, I'm going to move on to the first derivative, right? So the first derivative is going to tell us stuff about intervals of increase and decrease and local maximum, a possible local maximum or possible local minimum. So we're going to find the first derivative. Y prime is going to equal 3x squared plus 12x plus 9. 3x squared plus 12x plus 9. After you find the first derivative, you want to find your critical numbers. So we're going to set this equal to 0. I'm going to factor out a 3, x squared plus 4x plus 3. That will factor into x plus 3 and x plus 1. So our critical numbers happen at -3 and at -1. So those are critical numbers. So what we're going to do with those critical numbers is we are going to use the first derivative test here. And I'm going to put those in order on my number line, -3 and -1. And remember, what you're going to do is plug in a point in each one of those intervals into your factored derivative here. So if I plug in like -4, this 3 out front is always going to be positive, so I really don't need to worry about that. If that were negative, that will change the sign of what we're plugging in. But since that's just a positive 3, I'm going to kind of ignore that. If I plug in -4, both of these factors would give me negative values. So I would have a negative times a negative, which is positive. That tells me that our graph is going to be increasing on that interval. If I plug in something between -3 and -1, like -2, the x plus 3 would give me a positive value, and the x plus 1 would give me a negative value. So we have a negative here, which means we are decreasing on that interval. If I plug in something to the right of -1, like 0, both would be positive. So we have a positive here, which means we are increasing in that last interval from -1 to infinity. So what I'm going to write from that then is that the graph is increasing on the interval from -infinity to -3, and also -1 to infinity. It's decreasing on the interval from -3 to -1. There is a local maximum when we switch from increasing to decreasing. So there's a local maximum at -3. I'll find the y-coordinate here in just a second. There is a local minimum at -1. And again, we'll find the y-coordinate here in just a second. Okay. So how do we find those y-coordinates? Remember, if you want the actual coordinate point of your local max or local min, you need the y value. You need to go back to the original function and plug those in. So if I plug in -3, I already know that -3 is an x-intercept. I already know that the y-coordinate there is 0. So I know that my local max is at -3, 0. And I'm going to highlight that again to know that this is going to be a local maximum here. And then, so if I plug in -1, I'm going to get -1. And then +6 and -9. So that's going to give us a local minimum at -1, -4. So at -1, -4, I know we're going to have a local minimum here. Okay, we will move on to the second derivative. Okay, so the first derivative tells us all that information. The second derivative, y double prime, is going to be 6x plus 12. Just like the first derivative, I want to go ahead and set this equal to 0. Remember, these are not technically called critical numbers, but they are numbers of interest, possible inflection points. So if I solve this for x, I'm going to get x equals -2. And I'm going to, again, make this number line with -2. And we're checking concavity here. So if I plug in anything to the left of -2 into my second derivative, like -3, I would get a negative value here, which means this is going to be concave down. If I plug in anything to the right of -2, like 0, I'm going to get a positive value, which means we're going to be concave up to the right of -2. Because we changed concavity, there is going to be an inflection point there. So we're going to say that this is concave down on the interval from -infinity to -2, concave up on the interval from -2 to infinity. And again, because we switched concavity, there is going to be an inflection point here. So there's an inflection point at -2, comma, whatever we get when we plug in -2. Again, I'm going to go back to the original function here and plug in -2. And if I plugged in -2, we would have -8 plus 24 minus 18. That's going to give us a value of -2. So at -2, -2, we have an inflection point. Now again, we have, I guess, 4 coordinate points here, but they're very important coordinate points. So we found all this information, not only those specific points, but we know like what the graph looks like, right? So it's increasing from -infinity until I get to this -3. That's a local maximum. I also know that it's concave down from -infinity to -2, right? So until I get to this inflection point, my graph needs to be curving down. It hits a maximum here, but it continues to curve downward there. So I'm going to try my best to make that happen. But it's going to curve downward, hits a maximum here. It's still curving downward at that point, right? So it's curved downward that whole time, concave down, hits a local maximum at -3, and then it switches concavity and becomes concave up at that inflection point of -2. It hits a local minimum here. Again, my graph is still decreasing there, right? That's what this tells me right here. It's decreasing from -3 to -1. It's still going down there. Hits a local minimum, and then increases from -1 to infinity. It's still concave up over this interval, so it's still going to be curved upward, and it's just going to continue to go up to the right. It's going to look something like that. Now, I've gone ahead and graphed this in Desmos to see how close we are to that actual graph, and this is what it looks like. Okay, so pretty close here, right? So we've got a local maximum here at -3, also an x-intercept, inflection point at -2, -2, local minimum at -1, -4. Here's another intercept at 0, increasing, concave down. It's decreasing here. Switches to concave up here, and is concave up the rest of the way as we increase beyond -1. So again, the first and second derivative can help you find a lot of information about the shape of a graph